For number 18, we're dealing with section 6.3, where we're trying to create confidence intervals to estimate the population proportion, as opposed to 6.1 and 6.2, where we were estimating population means. So we're given information about a study, the number of people in the study, and the number who think the certain way about the question we were asking them. So our point estimate, our single value estimate for the population proportion, is just the proportion from the sample. So we get that point estimate by taking the number who thought a certain way, dividing by the total number in the sample, and that's the proportion of the sample who answered the certain way, which is our estimate for the population proportion. And the second part is asking for Q, which is our complement of the proportion. Again, we'll base it off our sample. So if our sample had this proportion answering a certain way, then 1 minus that would be the proportion in the sample who answered the other way. So our Q hat, our Q from our sample, is our point estimate for what Q for the entire population would be. Number 19 is similar to 18. We are going to have our information about our sample here, and we're going to find the point estimate for the population proportion, and all that's going to be is the proportion from the sample. So in our example here, 76 people in our sample out of the total number of people in our sample answered a certain way. And so that proportion of our sample, which will be our point estimate for the population proportion, is listed there. And then 1 minus that is our Q hat for our sample, and that is our estimate, our point estimate of what Q would be for the population. For 20, we will be creating some confidence intervals for a population proportion. Here's the number of people we surveyed, and here's the number in our sample that say they have made a New Year's resolution. And we're going to be constructing two different confidence intervals and comparing them. In 6.3, it has the formula for how you get the margin of error for a confidence interval of a population proportion. And notice our critical value has the Z here. We will be using the normal distribution here to find our critical values. And here it is zoomed in, so it's a little larger. Let's go into Excel now and calculate this margin of error. So here's the information about our sample, the number who said they've made a New Year's resolution out of the total sample size. So P hat, our sample proportion, just take the number who made the resolution and divide by the total sample size. That's P hat. And Q hat, the complement of that would just be 100% 1 minus the proportion who have made the resolution. So there's our P hat and Q hat. And now to find the critical value, we will be using the normal distribution. So your formula is norm.s.inv. And for a 90% confidence interval, that means there's 5% in each of the tails. If 90% is in between our critical values, that means 10% is outside, and split that between two tails, it's 5% in each tail. So we want to type in 5% here to find our critical value. Excel always gives the left-hand critical value, in this case marking 5% in the left-hand tail. By symmetry, the right-hand critical value is the same number as just positive, and we're going to want to use the positive one here in our formula. So now we know all the numbers to plug into the formula, our P hat, our Q hat, our sample size, and our critical value. And I'm going to break this up into chunks in Excel and get our margin of error E. The first thing I'm going to do here is our P hat times our Q hat divided by the sample size. After you get that result, you need to take the square root of that result. P hat times Q hat divided by the sample size, the square root of the result, and then whatever that square root's equal to, multiply it by the critical value. So the square root is that, and multiply that answer by the critical value, and you get your margin of error. Now you don't have to break it up into steps like I did. I just think it's easier and you're less likely to make a mistake. Here it is all written out in just one line here. You'll get the same result, but you just have to be careful with your symbols and parentheses to make sure Excel calculates it correctly. Once you have the margin of error, the sample proportion, p hat, is right smack dab in the middle of your confidence interval. You take that sample proportion, add the margin of error, that gives you the upper bound of the confidence interval. The sample proportion minus the margin of error is the lower bound. So this is our 90% confidence interval, and I'm going to go back and just tweak it to a 95% confidence interval for our second half of the problem. So this part's not going to change. What is going to change is we'll have a new critical value associated with 95% confidence. We would want to enter in 0.025, because if we have 95% between the critical values, that leaves just 5% in the tails, which is 2.5% in each of the tails. So we get our new critical value. And so our margin of error changes. And it's still that same formula, p hat times q hat divided by the sample size. Take the square root of that and multiply that by our new critical value. And so to get our confidence interval, we take the sample proportion that's in the very middle, add the margin of error to get the upper bound, sample proportion minus the margin of error to get the lower bound. So now if we want to compare these two confidence intervals to each other, we notice the 95% confidence interval is wider. It has a larger upper bound and a lower bound, so it has a wider range of numbers. And that should make sense. The way we are more confident that our interval actually does contain the population proportion is by including more numbers in the interval. We have a wider range of possible values, so we're more likely that the actual population proportion does lie somewhere within this range of numbers, so we can be more confident. So for these final parts, we just discussed that the 95% confidence interval is wider. That's why we have more confidence in it. And both intervals, any confidence interval can be interpreted like this. With the given level of confidence, we can say that the population proportion, in this case of adults who say they have made a New Year's resolution, that population proportion is between the endpoints, somewhere between this range of numbers for our given confidence interval. For 21, we'll be creating a confidence interval for a population proportion. Here is our survey data, the total number of people in the survey, and then the number of people in the survey who, in this case, started paying bills online in the last year. So here is the information about our sample, and we can find the sample proportion, p hat, take the number who paid bills online, divide by the total sample size, and then q hat, the complement of that would just be 1 minus p hat. The problem asks for a 99% confidence interval. So if we have 99% in between our critical values, that means there's just 1% split between the two tails, so 0.5% in each of the tails. To get the critical value associated with 0.5% in the normal distribution tail equals norm.s to inv, and 0.5% as a decimal, and you get the critical value. We'll want to use the positive one for our formula. And our formula to construct a confidence interval for a population proportion is listed here. We've solved for all of these values. Now we just need to plug them in. And plugging them in will give us the margin of error for our confidence interval. The first thing we want to do is our p hat times our q hat divided by the total sample size. After you've done that, take the square root of that answer and then multiply that square root answer by the critical value. And that's broken up into steps there. You could type it in all at once and you get the same result. So now for 99% confidence here, the sample proportion, that value we calculated earlier, is right in the very middle of our confidence interval. We take the sample proportion, add the margin of error to get the upper bound, and the sample proportion minus the margin of error to get the lower bound. And so we're 99% confident that the population proportion, in this case of adults who started paying bills online, is in between our endpoints here of our confidence interval. 22 will be similar to 21. We have the total number of people in our sample, and the number in this case who oppose a certain action, and we're going to create a 99% confidence interval for the proportion of the entire population who oppose that action as well. So here's our information of our sample. Start by finding the sample proportion p hat, the number who oppose divided by the total in our sample. Q hat is 1 minus that value. For a 99% confidence interval, we want norm.s.inv. And if there's 99% in between the critical values, there's 1% in the tails. So 0.5% in each tail. So the 0.5% as a decimal gives us our critical value. We'll want to use the positive version of that. The formula for our margin of error for our confidence interval with population proportions, we start by doing p hat times q hat and divide by the total sample size. Take the square root of that result, and then the result of the square root multiplied by the critical value. Or I like to break it into steps. You can type it in all at once. You get the same result. So our margin of error we have. And now to create our 99% confidence interval, we put the sample proportion right in the middle of the confidence interval, the upper bound, the sample proportion plus the margin of error, the lower bound, the sample proportion minus the margin of error. So we can say with 99% confidence that the population proportion of adults who oppose is in between these two endpoints here, somewhere within this range of numbers in our confidence interval. Number 23 is about finding the correct sample size in order to build a confidence interval for a population proportion with specified characteristics. In this example, we want 99% confidence in our confidence interval, and we want our point estimate to be accurate within 5% of the true population proportion. In other words, the margin of error for our confidence interval needs to be 0.05 for 5%. In 6.3, it shows us how to calculate the necessary sample size. If we have an estimate for p hat and q hat, we use them. If there is no estimate, then we use 0.5 for each of those values here in the formula. For the first part, we have no estimate, so we use 0.5 for each of them. We want 99% confidence, which means 99% is between the critical values. That means there's 1% in the tail, so 0.5% in each tail. So 0.005 is in the tails of our normal distribution. The margin of error was stated that we wanted it to be within 5%, so 0.05 is our margin of error. And so we're going to plug those four values in here to calculate the sample size we need. And I'm going to break it up into two steps in Excel. I'm going to do this division in squared, get an answer. I'm going to do this multiplication of p hat times q hat, get an answer. And then I'll multiply the two numbers together. And so the critical value divided by the margin of error, put that in parentheses, and then square the result. P hat times Q hat. And now that I have those two numbers, I'm just going to multiply them together to get the necessary sample size. Always we have to round upward. 663 is not enough, and we can't have a part of a person in our sample, so we would round up to 664. For part B, it's asking what the minimum sample size would be if we had a prior study that gave us an estimate here for p hat. So we'll use the estimate for p hat. 1 minus that value is q hat. Our critical value is going to stay the same for 99% confidence, same margin of error. Take the critical value, divide by the margin of error, and square it. Our p hat times q hat will get a new value there. And so multiplying those two results gives us our new necessary sample size, which again we round up to 647. And C, just compare your results, and this will always be the case. If we have an estimate for the population proportion, we have a p hat and q hat, it's always going to reduce the minimum sample size needed.